July 28, 1944. A British gunner pressed his eye against the sight of a 3.7-inch anti-aircraft gun as the distinctive, terrifying sound approached from across the channel. The pulse jet engine of a V-1 flying bomb cut through the morning air like a mechanical scream, growing louder with each passing second. He had fired hundreds of shells at these weapons over the past 6 weeks. The success rate was 17%. 83 out of every 100 flying bombs roared past his position untouched, continuing their deadly flight toward London, where each carried 850 kilograms of high explosive designed to detonate in the heart of a crowded civilian neighborhood. But on this morning, his ammunition was different. The shell loaded into his gun contained a fuse unlike anything the world had ever seen. A miniature radio transmitter packed with glass vacuum tubes that had somehow survived being fired at 20,000 times the force of gravity, a device that American scientists had spent 11 frantic months designing, testing, and manufacturing under conditions of absolute secrecy. What happened over the next 4 weeks would fundamentally alter the course of the V-1 campaign. The interception rate would climb from 17% to 74%, reaching 82% during peak operations. London would be saved from destruction, and the proximity fuse, a weapon that every major power had concluded was theoretically impossible, would prove to be one of the most decisive technologies of the Second World War. The story of how American engineers accomplished what German and British scientists had declared could not be done begins not in the summer of 1944, but in a shabby laboratory at the Carnegie Institution of Washington, where on August 24, 1940, a volatile physicist named Merle Tuvey was given an impossible deadline to solve an unsolvable problem. The National Defense Research Committee had been formed exactly 8 weeks earlier, on June 27, 1940. The fall of France had shocked American military planners into recognizing that the United States would inevitably be drawn into the spreading war. German and Japanese aircraft were decimating Allied forces. Anti-aircraft guns were proving catastrophically ineffective. The mathematics were brutal. At the start of the war, it required approximately 20,000 shells to down a single enemy aircraft. Some estimates ranged as high as 100,000 rounds per kill. The problem was straightforward to understand but seemingly impossible to solve. Conventional anti-aircraft guns used 2 types of fuses. The contact fuse detonated only if the shell directly struck the target, which required extraordinary accuracy against a maneuvering aircraft traveling at 300 miles per hour. The timed fuse was set to explode at a predetermined altitude, which required gunners to correctly estimate the target's future position, set the fuse accordingly, and hope the aircraft was exactly where predicted when the shell arrived. In practice, both methods failed spectacularly. Aircraft were too fast, too maneuverable, and too small. The sky was too vast. The margin for error was too slim. Allied ships and ground forces were being destroyed by aircraft that anti-aircraft guns could not reliably hit. The concept of a proximity fuse had tantalized weapons designers for decades. Imagine a fuse that could detect when it approached a target and detonate automatically. No need for perfect aim. No need for precise timing calculations. The shell would simply sense the aircraft and explode at the optimal distance. Simply, in theory. Impossible in practice given the technology of 1940, Germany had explored proximity fuses as early as 1930. By 1939, German researchers at 45 to say, Rheinmetall Borsig had developed over 30 different designs. They tested acoustic sensors that would trigger on-engine noise. They experimented with electrostatic detectors that would respond to the charged surfaces of aircraft. They built magnetic sensors. They constructed optical fuses using photoelectric cells. Every approach failed under combat conditions. Acoustic fuses couldn't distinguish between engine noise and wind noise. Electrostatic sensors were unreliable. Magnetic detectors had insufficient range. Optical fuses didn't work in clouds, fog, or darkness. Most fundamentally, None of the designs could withstand the violent forces of being fired from a gun. In 1940, as Hitler prepared Operation Barbarossa, the invasion of the Soviet Union, German leadership issued directives prioritizing only those weapons projects that could reach production within 6 months. Germany's proximity fuse programs were among the casualties. Rheinmetall Borsig would resume limited work in 1944, far too late to affect the war's outcome. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The British had reached further than the Germans. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a miniature Doppler radar system. In May 1940, William Butemont, Edward Shire, and Amherst Thompson submitted a formal proposal describing a radio-based proximity fuse. They understood the principle perfectly. A small transmitter in the shell would emit radio waves. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect, the same phenomenon that makes a train whistle sound different as it approaches and then recedes. When the reflected signal reached a specific frequency, indicating the target was within lethal range, an electrical circuit would close and detonate the shell. The theory was elegant. Making it work was another matter entirely. British engineers constructed prototype fuses in June 1940 and installed them in unrotated projectiles, the British cover name for solid-fueled rockets. Rockets faced far less severe acceleration than gun-fired shells. The tests were partially successful, but Britain's program was stymied by 2 critical obstacles. First, the cost was astronomical. Each prototype fuse required expensive components that Britain's wartime economy could barely afford. Second, and more fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available were those used in hearing aids, and these delicate components were still far too fragile to survive the violent acceleration of being fired from a gun. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was inadequate. Anti-aircraft gunners needed fuses that worked 95% of the time, or better. A 50% failure rate meant that half of all shells fired would be wasted, and in wartime, resources and lives depended on reliability. The British shared their research through the Tizard mission in late August 1940, when a team of British scientists travelled to the United States to exchange technological information. Among the secrets they carried was the complete circuit design for their radio proximity fuse. On September 17, 1940, Professor John Cockcroft met with Captain Wilford Goulett at the Naval Research Laboratory. 2 days later, Cockcroft explained the British work in detail to Dr. Merle Tuve of the Carnegie Institution. Tuve was 40 years old, a brilliant physicist with a reputation for volatile temperament and absolute intolerance of bureaucratic delays. He immediately recognized both the potential and the challenge. If proximity fuses could be made to work reliably, they would revolutionize anti-aircraft warfare. But the engineering problems were formidable. On August 12, 1940, 12 days before, Tuve's formal appointment as chairman of Section T, Captain Gilbert Hoover of the Bureau of Ordnance, had presented the Navy's requirements. They needed rugged proximity fuses that could withstand the immense forces of anti-aircraft artillery fire, with directional capabilities to focus shell fragments toward the target. Hoover had asked for a lot. He was asking for the impossible. Consider what had to be accomplished. The fuse had to fit inside the nose of a 5-inch artillery shell, leaving room for 7 pounds of high explosive. Inside this limited space, engineers had to fit a complete radio transmitter and receiver, a power source, safety mechanisms to prevent premature detonation, and a detonator. All of this had to function in extreme temperatures, survive storage for months, and remain reliably under combat conditions. Most daunting of all, it had to withstand the shock of being fired from a gun. When a 5-inch shell is fired, it accelerates from 0 to 2,800 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity. Every component experiences a crushing force equivalent to being hit with a sledgehammer traveling at highway speed. The shell simultaneously begins spinning as it passes through the rifled barrel. Within milliseconds, it reaches 25,000 revolutions per minute. The centrifugal force is enormous. Any component not perfectly secured will be torn apart. And after surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target. The radio had to transmit, the receiver had to detect reflections, the circuit had to calculate the correct detonation point, the explosive had to fire. Every major power that examined the problem concluded it was theoretically impossible. The forces were too great, the components were too delicate, the engineering tolerances were too tight, the manufacturing complexity was too high. Merle, Tuve decided to do it anyway. On August 24, 1940, Tuve formally assumed leadership of Section T at the Carnegie Institution's Department of Terrestrial Magnetism in Washington. He assembled a small team of physicists and engineers. Among them was Richard Roberts, who began immediately duplicating the British circuit designs. Lloyd Berkner developed an improved version using separate transmitter and receiver circuits, which offered better control and higher power. In December 1940, Tuve invited Harry Diamond and Wilbur Hinman from the National Bureau of Standards to join the project. Diamond was a radio engineer with extensive experience in miniaturized electronics from his work on radiosondes, weather balloons that transmitted atmospheric data. In just 2 days, Diamond developed a new Fuze design based on Berkner's concept. The team settled on a radio-based system operating at approximately 180 to 220 MHz. The transmitter would emit continuous radio waves. When these waves struck a target, they would reflect back with a slightly different frequency due to the Doppler effect. The receiver would detect this frequency shift and trigger detonation when it reached a predetermined value. The physics were sound. The engineering was the challenge. Tuve posted a series of dictates on the laboratory walls that captured the urgency and priorities of the project. I don't want any damn fool in this laboratory to save money. I only want him to save time. Shoot at an 80% job. We can't afford perfection. Don't try for an A. In a war, D is necessary and enough, but an F is fatal. Late. These were not the principles of normal scientific research. They were the principles of wartime engineering under impossible deadlines. Perfection was the enemy. Speed was everything. A weapon that worked 80% of the time and arrived in 6 months was infinitely more valuable than a weapon that worked perfectly and arrived in 2 years. The Navy had made clear that every month's delay in developing a proximity fuse was equivalent to losing a cruiser. Enemy aircraft were sinking Allied ships, soldiers were dying, cities were being bombed. The pressure was immense. The first challenge was the vacuum tubes. The fuse needed miniature tubes that could withstand 20,000 G-forces while continuing to function. In 1940, the smallest available vacuum tubes were those used in hearing aids, manufactured by companies like Raytheon and Sylvania. These tubes were designed to sit gently in someone's pocket, not to be fired from a cannon. James Van Allen, a young physicist, who would later discover the radiation belts surrounding Earth that bear his name, took on the task of developing what the team called rugged vacuum tubes. He started with the hearing aid tubes and redesigned them from first principles. The glass envelopes were thickened and carefully annealed to resist shattering. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections, to withstand vibration and shock. The tubes were potted in wax inside the fuse body, which cushioned them against acceleration forces. Every aspect was tested by firing complete fuses from a vertical gun into soft earth at the Naval Proving Ground in Dahlgren, Virginia. The earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see exactly what had broken. Filaments snapped. Grids cracked. Glass envelopes shattered. Solder joints failed. Through hundreds of test firings and thousands of design iterations, the team gradually developed tubes that could survive. It was painstaking work. Each failure revealed a new weakness. Each modification required new tests. The engineers were literally learning how to make electronics withstand forces that electronics had never been designed to endure. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized initial production tooling. The engineers were confident they could improve reliability during the production ramp-up, and they were right. But vacuum tubes were only one challenge among many. The fuse needed a power source. Conventional batteries were too large and had limited shelf life, particularly in the tropical heat of the Pacific Theater where the Navy would deploy them. Engineers developed a reserve battery using a liquid electrolyte kept separate from the battery plates until the moment of firing. When the shell was fired, centrifugal force from the spinning shell pushed the electrolyte outward into contact with the metal plates. This generated electricity through chemical reaction. The design was brilliant in its simplicity. The battery had indefinite storage life because the chemicals were kept separate. Only the violence of being fired activated it. The fuse needed multiple safety mechanisms. It could not arm until the shell was well clear of the gun, otherwise it might detonate near the ship or the gun crew. It required protection against accidental detonation from radio interference or the ship's own radar systems. It needed wave suppression circuitry to prevent premature detonation when fired at low angles over water, where reflections from the ocean's surface could trigger the fuse. Each safety feature added complexity. Each component increased the risk of failure. Each additional circuit meant more vacuum tubes, more wiring, more connections that could break under stress. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components. The Mark 32 fuse for the Navy's 5-inch gun was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. On May 6, 1941, exactly 9 months after Fuze assumed leadership of Section T, the team achieved their first success. Harry Diamond and Wilbur Hinman built 6 proximity fuses, installed them in air-dropped bombs, and successfully tested them over water. The bombs detonated at the correct altitude without any contact or timing mechanism. The fuses had detected the water surface, calculated the optimal detonation height, and triggered the explosives. It was a milestone, but bombs were not the primary objective. Bombs faced acceleration forces of perhaps 100 Gs. Artillery shells faced 20,000 Gs. Making the fuse work in bombs proved the concept. Making it work in artillery shells required solving problems that were exponentially more difficult. The team split their focus. Work continued on bomb and rocket fuses, which the Army desperately needed. But the Navy's priority remained anti-aircraft shells, and Section T concentrated its best engineers on solving the artillery problem. Through the summer and fall of 1941, components gradually came together. Sylvania Electric Products modified their hearing aid tubes to withstand higher forces. The National Carbon Company, later Energizer, perfected the reserve battery design. Radio Corporation of America developed the transmitter circuitry. Dozens of companies contributed specialized components. By September 1941, after 11 months of frenzied effort, a complete fuse functioned properly at the end of its trajectory in a test firing. The team had achieved what German and British scientists had concluded was impossible. They had built a radio that survived being fired from a gun. On January 18, 1942, the Navy awarded a production contract for a basic model of the Fuze. But the weapon still needed extensive testing under realistic combat conditions. In August 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was radio-controlled drone aircraft, small unmanned planes that simulated enemy bombers. Using conventional ammunition, downing these maneuvering drones typically required dozens of shots. The drones were designed to be difficult targets, mimicking the speed and maneuvers of actual combat aircraft. Cleveland's gunners loaded proximity-fused shells and took aim. They fired 4 bursts. All 3 drones were destroyed. The Navy observers were stunned. The drone operators were devastated. They had never seen any of their drones completely annihilated before. The proximity fuses had turned near misses into kills. Shells that would have harmlessly exploded hundreds of feet from their targets instead detonated at precisely the optimal distance, spraying shrapnel through the drones and tearing them apart. The Navy immediately cancelled the remainder of the scheduled tests. There was no need for further proof. The proximity fuse worked. More importantly, it worked far better than even its designers had dared hope. Production ramped up rapidly. 5 companies were selected as primary manufacturers: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Over 100 additional firms participated in component production. The Crosley Corporation in Cincinnati, Ohio, became the largest single producer. At peak output, the company employed 10,000 workers operating continuously, 7 days a week, producing 16,500 fuses daily. Massachusetts produced even more vacuum tubes than Crosley produced complete fuses, manufacturing 95% of all miniature vacuum tubes used across the entire program. Thousands of workers, many of them women, assembled the intricate components under conditions of absolute secrecy. Workers signed secrecy oaths and were searched entering and leaving the facilities. They did not know what they were building. They knew only that their work was classified at the highest levels and that the war's outcome might depend on their precision. Security surrounding the proximity fuse was second only to the Manhattan Project. The device was given the deliberately misleading code name VT Fuze, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. The very existence of the fuse was classified top secret. Even the use of the fuse in combat was initially restricted to situations where there was no chance of a dud shell falling into enemy hands. If Germany or Japan captured an intact proximity fuse, their engineers might reverse engineer the technology or develop countermeasures. If Germany equipped its anti-aircraft guns with proximity fuses, intelligence analysts estimated Allied bomber losses could increase by 300%. The strategic air campaign might become impossible, so the fuses were used only over water, where dud shells would sink beyond enemy reach. When a proximity-fused shell accidentally landed on Sicily during the invasion in July 1943, headquarters immediately dispatched a special patrol to recover it before German forces could find it. The first combat use came on January 5, 1943, off Guadalcanal in the Solomon Islands. 4 Japanese Aichi dive bombers attacked a United States Navy task force. As the aircraft broke off their attack, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the cruiser USS Helena, fired salvos of proximity-fused shells at the departing bombers. The shells exploded near one of the aircraft, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners had achieved what would have required dozens of conventional shells. They had downed an enemy aircraft without scoring a direct hit. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. The weapon was so effective that it fundamentally changed naval tactics. Ships could now defend themselves against aerial attack with confidence. Carriers could operate closer to enemy territory. Amphibious landings could proceed with less fear of air attack. The proximity fuse was silently altering the balance of power in the Pacific War, but for most of the war, the Pentagon strictly forbade use of the fuse over land. The risk of a dude falling into enemy hands was considered too great. German engineers were exceptionally skilled. If they obtained even one intact proximity fuse, they might duplicate the technology within months. German anti-aircraft guns equipped with proximity fuses would devastate Allied bomber formations. The strategic air campaign against Germany might fail. This absolute security restriction began to crack in June 1944, when Germany unleashed a new terror weapon against London. On June 13, 1944, 1 week after the D-Day landings, the first V-1 flying bomb struck London. It hit a railway bridge in Bethnal Green at 4:04 in the morning. 6 people died. The V-1 campaign had begun. The Vergeltungswaffe 1, Vengeance Weapon 1, was unlike anything the Allies had faced before. It was a pilotless aircraft, what today would be called a cruise missile. 8 meters long with a wingspan of 5.3 meters, powered by an Argus pulse jet engine that produced a distinctive, terrifying buzzing sound. The V-1 flew at speeds up to 400 miles per hour at altitudes between 2,000 and 3,000 feet. It carried 850 kilograms of high explosive in its nose, set to detonate on impact. The guidance system was primitive but effective enough. A magnetic compass maintained heading. An aneroid barometer controlled altitude. A small propeller on the nose counted down the distance traveled. When the propeller reached a predetermined number of rotations, corresponding to the distance from launch site to target, the engine cut off and the weapon dove toward the ground. Londoners quickly learned to fear the characteristic sound. As long as they could hear the pulse jet engine, they were safe. When the engine cut off, they had perhaps 15 seconds to find shelter before impact. The sudden silence was more terrifying than the noise had been. Between June and early September 1944, Germany launched over 9,000 V-1 Segundo against Britain, an average of 120 per day. The psychological impact was devastating. Unlike bombers, which came in waves and could be detected by radar providing warning time, the V-1 Segundo arrived individually and without pattern throughout the day and night. There was no respite, no safe time. The terror was constant. British defences initially consisted of anti-aircraft guns, barrage balloons with trailing cables to snag the missiles, and fighter aircraft attempting to intercept the bombs before they reached London. The results were discouraging. In the first weeks of the campaign, British defences destroyed only 17% of the V-1 Segundo that entered the coastal gun belt. 83% got through. The mathematics were brutal. For every 100 V-1 Segundo launched, 83 detonated in London, each carrying nearly a ton of high explosive into crowded civilian neighbourhoods. Tens of thousands of casualties. Massive destruction of London's already battered housing stock. The British scrambled to improve their defences. Anti-aircraft guns were repositioned to create a concentrated belt along the coast. Radar systems were upgraded. Fire control computers were installed. Fast fighter aircraft, particularly the Hawker Tempest, shot down hundreds of V-1 Segundo, but the fundamental problem remained. Hitting a small, fast-moving target was extraordinarily difficult. Conventional anti-aircraft shells used timed fuses that had to be set correctly for altitude and time of flight. Given the V-1's speed and small size, accuracy was poor. On June 12, 1944, Prime Minister Winston Churchill made a decision that broke 4 years of absolute secrecy. He authorised the use of proximity fuses in anti-aircraft guns defending Britain against the V-1 threat. The risk calculation had changed. Yes, there was danger that a DUD proximity fuse might fall into German hands. But the alternative was London being destroyed by V-1 Segundo. The terror weapon had to be stopped, and proximity fuses offered the best chance of success. Section T at the Applied Physics Laboratory, which had relocated from the Carnegie Institution to larger facilities in Silver Spring, Maryland, immediately began modifying fuses specifically for the V-1 threat. The modifications were critical. The V-1 was smaller and faster than the aircraft the fuses had been designed to intercept. The radar had to be calibrated for a smaller radar cross-section. The detonation threshold had to be adjusted for the V-1's flight profile. Modified fuses were rushed into production at Crosley Corporation in Cincinnati and other facilities. British Prime Minister Churchill personally authorized a special flight of Lancaster bombers to transport the fuses from Cincinnati directly to Britain, bypassing normal shipping channels to save time. In mid-July 1944, approximately 500 anti-aircraft guns along the English Channel were equipped with proximity-fused ammunition. The guns were positioned specifically on the coast, where their fire would not endanger Royal Air Force fighter aircraft operating over land. The proximity fuses were paired with newly developed SCR-584 fire control radar systems and improved gun directors. The effect was immediate and dramatic. In the first week of using proximity-fused ammunition, the destruction rate climbed from 17% to 24%. The improvement seemed modest but represented a 41% increase in effectiveness. More importantly, it demonstrated that the system was working. Engineers and gunners rapidly refined their techniques. Radar operators learned to track the small, fast V-1 segundo more accurately. Gun crews learned the optimal firing patterns. Fire and control computers were fine-tuned for the V-1's specific flight characteristics. The proximity fuses themselves were adjusted based on combat experience. By the second week, the destruction rate reached 36%. By the third week, 55%. The learning curve was steep. Every day brought improvements. By the end of the fourth week of operations, anti-aircraft shells, equipped with proximity fuses, accounted for the destruction of 79% of all incoming V-1 segundo. The transformation was staggering. In the space of 1 month, British anti-aircraft defences had gone from near helplessness to devastating effectiveness. More than 3 out of every 4 V-1 segundo were being destroyed before reaching their targets. On August 28, 1944, during peak operations, the interception rate reached 82%. On this single day, radar detected 104 V-1 missiles approaching the coast. 68 were destroyed by proximity-fused anti-aircraft fire. Of the remaining 36, fighter aircraft and barrage balloons accounted for additional kills. Only 4 V-1 segundo reached London. 4 impacts instead of 104. The proximity fuse had not just improved British defences, it had fundamentally transformed them from inadequate to overwhelming. The psychological impact on both sides was profound. Londoners, who had lived in terror for weeks, began to feel hope. The distinctive buzz of the V-1 engines was increasingly followed not by the dreaded silence and explosion, but by the sound of anti-aircraft fire and mid-air detonations. People could see the missiles being destroyed. The enemy's terror weapon was being defeated. For German forces operating the V-1 launch sites, the realization was devastating. They had expected the V-1 campaign to break British morale and force Churchill to negotiate. Instead, their supposedly unstoppable weapon was being systematically destroyed. Intelligence reports from agents in Britain described the dramatic improvement in British anti-aircraft effectiveness, but German analysts could not determine the cause. They knew the British had improved their fire control systems and radar. They suspected better ammunition, but they did not know about the proximity fuse. The American weapon remained secret even as it destroyed thousands of German missiles. The success against V-1 segundo finally convinced military leadership to lift restrictions on land use of proximity fuses. The weapon was simply too effective to continue withholding from ground forces. If proximity fuses could destroy pilotless missiles, they could certainly devastate enemy aircraft and ground forces. On October 25th, 1944, the Combined Chiefs of Staff formally approved unrestricted use of proximity fuses over land. Anti-aircraft guns defending the vital port of Antwerp, recently captured by Allied forces, were immediately equipped with proximity-fused ammunition. If you find this nation's story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Antwerp was critical to supplying Allied armies advancing toward Germany. Germany responded by redirecting V-2 from London to Antwerp, launching over 2,500 missiles at the port. When German engineers modified the V-2 to fly as low as 1,200 feet, making interception vastly more difficult, applied physics laboratory physicists quickly designed new fuse modifications for 3.7-inch and 90mm anti-aircraft shells. The modified fuses were rushed into production at Crosley Corporation. Churchill personally authorized another special Lancaster flight to transport them to Antwerp. A single anti-aircraft battalion destroyed 48 of the first 75 V-2 they encountered using the new ammunition. The port remained operational throughout the critical supply period, but the most dramatic demonstration of the proximity fuse's effectiveness came not from anti-aircraft use, but from field artillery. On the morning of December 16, 1944, more than 200,000 German troops and nearly 1,000 tanks launched Operation Watch on the Rhine, Hitler's last desperate offensive in the West. The Germans struck through the Ardennes forest, aiming to split Allied armies and capture Antwerp. The offensive took the Allies by complete surprise. Colonel George Axelson, commander of the 406th Artillery Group, faced an agonizing decision that morning. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armoured cavalry desperately needed artillery support. Axelson had just received proximity-fused shells, codenamed Posset by the army, but Supreme Commander Dwight Eisenhower had not yet authorized their use over land. Axelson decided the emergency trumped the restrictions. He ordered his gunners to fire the Posset, proximity-fused shells. The effect on German forces was devastating. For the first time in the European theatre, American artillery was firing air bursts with perfect consistency, regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. Foxholes provided no protection. Traditional defensive tactics, developed over years of warfare, suddenly became obsolete. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like it. They could not hear the shells approaching due to the high velocity of American artillery. The first warning was the explosion overhead. There was no time to take cover, no place to hide. The proximity-fused shells turned every open area into a killing field. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Over the next 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theatre. The impact on German forces was immediate and catastrophic. Lieutenant General George Patton later wrote to the War Department describing an action near the Sauer River. His Third Army had caught a German battalion attempting to cross the river with a concentrated barrage of proximity-fused shells. By actual count, 702 enemy soldiers were killed. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies had this weapon, they would need to devise entirely new methods of warfare. He added with evident satisfaction, "I am glad that you all thought of it first." The morning of December 21st saw proximity fuses, used in the defense of Malmedy. American artillery battalions supporting the town fired proximity-fused shells with devastating effect. The airbursts, so unnerved the attackers that some charged directly into American positions, seeking any shelter from the overhead explosions. The attack was repelled. German prisoners of war, interviewed by American intelligence officers, captured the psychological impact. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer, focused on the Breitli-Steel implications for air defense. If Germany had possessed proximity fuses, he estimated the Allied strategic bombing campaign would have become unsustainable. At loss rates of 15 to 20% per mission, the combined bomber offensive would have ground to a halt. But he immediately added that Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate over $1 billion 1940s dollars to a single weapon system and mobilize over 100 factories. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match. The Battle of the Bulge demonstrated how American doctrine had evolved to maximize the fuse's effectiveness. Forward observers called down fire not just on visible targets, but on suspected positions. Artillery batteries laid down barrage patterns covering entire areas. The proximity fuses meant that every shell was an effective airburst. German tactical doctrine had to be completely rewritten. Traditional defensive positions were suddenly death traps. Moving in the open during artillery fire was suicide. The Germans tried to adapt by dispersing more widely and staying constantly on the move. But adaptation had limits. The proximity fuse fundamentally altered the equation. German soldiers began to exhibit what American intelligence termed artillery shock syndrome, a condition specifically triggered by the helplessness of facing proximity-fused fire. Some units experienced discipline problems, with soldiers refusing orders to move into areas under American artillery coverage. American intelligence reports noted that German commanders were offering rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. By January 1945, Wright Field in Ohio had developed electronic countermeasure systems designed to jam the fuse's radio signals, based on the assumption that captured fuses would lead to German jamming efforts. But German engineers never fully grasped what they had captured. Having concluded years earlier that radio-based proximity fuses were impossible given artillery acceleration forces, they never recognized that miniature radio transmitters were inside every shell. Some German analysts theorized that the Americans had developed superior mechanical time fuses with better accuracy. Others speculated about new types of explosives that produced larger fragmentation patterns. The truth, that each shell contained a complete miniature radar system that had been fired at 20,000 G-forces and continued to function perfectly, remained beyond their comprehension. It was not that German scientists lacked the theoretical knowledge. They understood radio. They understood radar. They had explored proximity fuse concepts in the 1930s. But they had correctly calculated that the engineering challenges were insurmountable with available technology and resources. What they failed to anticipate was that American industry would develop entirely new manufacturing techniques, new quality control systems, and new training programs that made the impossible achievable. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impossible barrier. Ground combat intensified as well. During the Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity phases set to detonate at rooftop level showered entire city blocks with shrapnel, making defensive positions untenable. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe would have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defences equipped with proximity fuses might have made D-Day landings unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance. The proximity fuse had not just contributed to Allied victory, it might have been essential to making victory possible. The production statistics were staggering. By war's end, American industry had produced more than 22 million proximity fuses at a total cost exceeding $1 billion 1940s dollars, equivalent to approximately $15 billion today. This made it the third most expensive weapons program of the war, after the Manhattan Project and radar development. At peak output, American factories were producing 70,000 fuses per day. That represented nearly 3 billion individual components manufactured to precise specifications, assembled by hand under microscopes, tested, and shipped to combat theaters around the world. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, increased efficiency, and economies of scale that would later revolutionize the electronics industry. At $18 per fuse, the weapon was expensive, but not prohibitively so. The increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, paying extra for a fuse that multiplied effectiveness was obvious value. The secrecy was so complete that production workers at different factories did not know other facilities were building the same components. Suppliers manufactured parts without understanding their purpose. The security classification remained in force until September 1945, when the war ended and the proximity fuse was finally revealed to the public. The technological legacy of the proximity fuse extended far beyond military applications. The miniaturization techniques influenced the entire electronics industry. Before the proximity fuse, most electronic devices used large vacuum tubes and bulky components. The fuse required everything to be miniaturized, creating demand for smaller components and better manufacturing techniques. The quality control methods developed for proximity fuse production became standard practice in manufacturing. Statistical process control, automated testing procedures, and rigorous inspection protocols were all pioneered or refined during the fuse program. These methods would later become foundations of modern manufacturing across all industries. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training and supervision. Tens of thousands of workers, many with only high school education, were trained to assemble intricate electronic devices under microscopes. This challenged prevailing assumptions about technical work and helped democratize the electronics industry in the post-war period. The scientists and engineers who worked on the proximity fuse went on to distinguished careers. James Van Allen, who developed the rugged vacuum tubes, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958 and credited with discovering the Van Allen radiation belts, used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. The entire field of space electronics traces its lineage back to the work done in 1940 and 1941 by engineers who needed to make radio transmitters survive forces that should have destroyed them. Merle Tuve continued leading scientific research at the Carnegie Institution. Lloyd Berkner became a prominent figure in space science and ionospheric research. Dozens of others joined universities, industrial laboratories, and government research facilities, bringing expertise in miniaturization, electronics, and systems engineering that would shape American technology development throughout the second half of the 20th century. The industrial infrastructure created for fuse production found new uses after the war. Factories that had manufactured vacuum tubes converted to producing television tubes and consumer electronics. The Crosley Corporation, which had produced over 5 million proximity fuses during the war, transitioned to manufacturing radios, televisions, and appliances. Sylvania Electric Products leveraged its vacuum tube expertise to become a major supplier to the emerging television industry. Workers trained in precision assembly became the workforce for the emerging electronics industry. Supply chains established for fuse components supported the growth of consumer electronics markets. The organizational knowledge and manufacturing techniques developed during the war accelerated the development of commercial electronics by perhaps a decade. The story of the proximity fuse is ultimately a story about resources, priorities, and the different paths nations took through World War II technology development. Germany invested heavily in advanced weapons like jet aircraft, ballistic missiles, and rockets. These were impressive achievements that pushed the boundaries of what was technically possible, but they came too late and in too few numbers to affect the war's outcome. The Messerschmitt 262 jet fighter was superior to any Allied aircraft, but Germany produced fewer than 1,500 before the war ended. The Vedos ballistic missile was a technological marvel, but produced no military advantage commensurate with its enormous development cost. America invested in technologies that could be mass-produced immediately. Proximity fuses, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability over theoretical perfection. The result was a weapon available in overwhelming numbers when needed. This reflected a fundamental difference in strategic thinking. Germany sought war-winning superweapons that would offset Allied numerical superiority. America sought effective weapons that could be produced in quantities that made numerical superiority overwhelming. The proximity fuse was not a superweapon. It was a very good weapon produced in very large numbers. That approach proved decisive. In the final accounting, the proximity fuse represented everything that made American industrial power dominant in World War II. It combined advanced technology with practical engineering. It required massive investment, but produced proportionate results. It was sophisticated yet manufacturably, effective yet affordably at scale, innovative yet reliably. It was a perfect example of how America fought and won World War II. By solving impossible problems through the application of extraordinary resources, brilliant engineering, and an industrial base that could produce technological miracles by the millions. The 11 months from August 1940, when Merle Tuve assumed leadership of Section T, to June 1941, when the first successful bomb tests were conducted, represented one of the most remarkable engineering achievements of the war. A small team of scientists and engineers, working under impossible deadlines with inadequate resources, accomplished what the world's experts had declared could not be done. They miniaturized complex electronics. They made delicate vacuum tubes survive forces that should have destroyed them. They developed manufacturing processes that enabled mass production of sophisticated electronic devices. They created quality control systems that ensured reliability under combat conditions. They did all of this while maintaining absolute secrecy and coordinating work across more than 100 factories. The German soldiers who faced proximity-fused fire understood this implicitly. Wehrmacht veterans interviewed after the war consistently described the fuse not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national will. One former Wehrmacht officer, repatriated in 1946, captured this understanding perfectly. He described the proximity fuse as the weapon that finally made him comprehend that Germany had lost the war, not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem that Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources that Germany could not match. If America could build miniature radios that fit inside artillery shells and worked after being subjected to forces that would destroy normal electronics, what else could they build? The officer's conclusion was that Germany had been fighting a war of the 20th century, with 19th century assumptions about what was possible. Germany had exceptional scientists, brilliant engineers, and sophisticated industry, but Germany's economy was mobilized for total war, with every resource committed to immediate military production. There was no surplus capacity for ambitious development programs that might not yield results for years. America, by contrast, had surplus capacity. The American economy was so vast that it could simultaneously wage war on two fronts, supply allied nations through Lend-Lease, maintain civilian production at near pre-war levels, and invest over $1 billion in a single weapons program that might fail. The proximity fuse succeeded because America could afford 11 months of intensive research with no guarantee of success. It succeeded because American industry could dedicate 100 factories to producing a single type of component. It succeeded because thousands of workers could be trained to perform complex assembly tasks. It succeeded because the American economy could absorb the cost of producing 22 million sophisticated electronic devices, even though many would never be used. This comprehensive advantage in resources extended beyond production to research and development. Section T eventually employed over 1,000 scientists, engineers, and support staff. Dozens of universities contributed research. Industrial laboratories provided expertise. The program had access to the best minds in American physics and engineering, pulled from academic positions and industrial jobs, given unlimited budgets, and told to solve the problem as quickly as possible. German proximity fuse research, by contrast, was shut down in 1940 to free resources for weapons that could enter production within 6 months. When Rheinmetall Borsig resumed work in 1944, they developed hundreds of working prototypes. German engineers proved the concept was achievable. But by then, Germany lacked the industrial capacity to establish mass production, and the resources required would have competed with production of tanks, aircraft, and basic ammunition. The proximity fuse perfectly encapsulated the material reality of World War II. Germany and Japan fought with skill, determination, and technological sophistication, but they fought an enemy with resources so vast that American advantages in sheer productive capacity could overwhelm any tactical or technical edge. The Battle of the Bulge demonstrated this reality. German forces achieved complete tactical surprise. They struck in terrible weather that grounded Allied air power. They caught American forces in prepared defensive positions and achieved favorable terrain, and they were crushed by artillery. American gunners, equipped with proximity-fused shells, simply called down fire on German positions and obliterated them. The Germans adapted their tactics, dispersed their forces, and changed their approach, but artillery followed them everywhere. The sheer volume of American fire, combined with the devastating effectiveness of proximity fuses, made German resistance ultimately futile. By March 1945, German units were essentially paralyzed by fear of American artillery. Units would not move during daylight. They avoided any position that appeared to be a likely target. Morale plummeted. The sense of helplessness broke the will to resist. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender. Not the fear of death, which soldiers accepted, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. This was psychological warfare at its most effective, accomplished not through propaganda, but through demonstrated futility of resistance. German soldiers were professional, experienced, and well-trained, but they were being systematically destroyed by weapons they could not effectively counter, produced in quantities they could not match, by an enemy whose industrial capacity seemed limitless. The final months of the war saw American proximity fuse production actually increasing even as the war wound down. Factories continued operating at peak capacity. New production lines were being established. The manufacturing infrastructure was so robust that it could have continued producing proximity fuses indefinitely. This surplus capacity itself sent a message: America could afford to produce weapons faster than they could be used. Germany was desperately trying to produce enough ammunition to continue fighting. The contrast was stark and psychologically devastating. Post-war analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war. Estimates suggest the fuse saved tens of thousands of Allied lives by reducing the length of campaigns and increasing the effectiveness of defensive operations. Against kamikaze attacks in the Pacific, proximity fuses were credited with preventing ship losses that would have significantly delayed operations. The strategic impact was multiplied by production scale. Because fuses were available in unlimited quantities by late 1944, they could be used without conservation. Fire missions that would have been questionable with conventional ammunition became routine. The 11 months that Merle Tuvey and his team spent developing the proximity fuse changed warfare forever. Modern anti-aircraft missiles, surface-to-air defense systems, and even some air-to-air missiles still use proximity fuses based on the same fundamental principles developed in 1940 and 1941. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys. They can operate in jamming environments. They can adjust their detonation parameters in real time based on target characteristics. But the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The physics Merle Tuvey's team worked out in 1940 are still the physics that govern modern proximity fuses. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. It proved that the greatest victories come not from seeking the impossible, but from making the necessary possible through sheer force of will and unlimited application of resources. The weapon that every major power had concluded was impossible became the weapon that changed warfare. American scientists, engineers, factory workers, and military personnel accomplished what the world's experts declared could not be done. They miniaturized complex electronics, made delicate vacuum tubes survive artillery forces, and manufactured the result by tens of millions. The proximity fuse ended Germany's ability to terrorize London with V-1 missiles. It devastated German forces during the Battle of the Bulge. It protected Allied naval forces from kamikaze attacks in the Pacific. It demonstrated American technological and industrial superiority in the most tangible way possible. And it did all of this because one volatile physicist in August 1940 decided that 11 months was enough time to solve the impossible. Merle Tuvey looked at the problem, examined the available resources, considered the stakes, and simply decided that failure was not acceptable. His dictate posted on the laboratory walls captured the entire philosophy. The best job in the world is a total failure if it is too late. Tuvey and his team did not create the perfect proximity fuse. They created the adequate proximity fuse in time to matter. That, a distinction made all the difference. A perfect weapon delivered in 1946 would have been useless. An 80% weapon delivered in 1942 saved tens of thousands of lives. The story of the proximity fuse is the story of engineering under pressure. It is the story of accepting good enough when perfect is impossible. It is the story of massive industrial mobilization guided by scientific excellence. It is the story of thousands of people from Nobel Prize-winning physicists to factory workers with high school educations, all contributing to a single goal. Most importantly, it is the story of what happens when a free society marshals its resources against an existential threat. American industry produced 22 million proximity fuses because American democracy mobilized to win a war. Workers assembled them because they understood the stakes. Scientists designed them because they recognized the necessity. Companies manufactured them because the nation demanded it. The 11 months from concept to working prototype represented not just an engineering achievement, but a demonstration of social capacity. America could organize, coordinate, innovate, and produce on a scale that totalitarian powers could not match. The proximity fuse proved that democracy, properly mobilized, could outproduce, out-innovate, and outfight any dictatorship. That lesson resonates far beyond World War II. In 1940, facing an impossible problem with inadequate time and limited resources, American engineers simply decided to solve it anyway. They built the weapon that could not be built. They produced it in quantities that should have been impossible. They deployed it in time to change the war's outcome. And in doing so, they proved that with sufficient determination, adequate resources, and brilliant engineering, nothing is truly impossible. The proximity fuse exists as permanent testament to that truth. Thank you for watching. For more detailed, historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.